This video is about graphics, vector graphics and raster graphics. It corresponds to section 7.10.1 of the Applied Analog Electronics textbook. Now, graphics get used a lot in design reports, and there's basically 2 or 3 flavors of graphics that we use. We use diagrams like block diagrams and schematic diagrams, and we use graphs generally produced from some drawing tool like GNUplot or MATLAB or Matplotlib or R, and even a number of other different graphics programs that produce plots. And finally we have photographs. And these different types of images that get included in design reports call for somewhat different file formats and different representations in the computer. There's basically 2 different flavors of representation for these graphic images. They're vector graphics and raster graphics. And the difference is that vector graphics consists of lines and polygons and other simple geometric objects, sometimes arcs and circles. And so they're the appropriate type of representation for things like schematic diagrams and block diagrams and even plots that are functions that are being plotted, because these geometric specifications are high precision. They tell you precisely what it can be, and you can zoom in, and the thing still stays well defined. You don't have blurring or fuzziness as you zoom in, so you can have a crisp line that stays a line as you zoom in arbitrarily. The other type of graphics, raster graphics, are what you get from a scan or a photograph. And those basically are an array of dots, is what it amounts to, though you can think of them as being a grid of pixels. And each pixel has got a color or darkness associated with it, depending whether it's a color or black and white sort of image. And in these raster graphics, you can get very complicated images, but you can't get very high precision. That is to say, if you keep zooming in, at some point you start just seeing the individual pixels. Raster graphics also generally tend to be big. They can be compressed somewhat, and the standard formats that people use do some compression in order to try and save memory space. But there are limitations on how much you can do that without the image quality being degraded. The formats that you generally see for representing graphics, the file formats, tend to be associated with one or the other of these formats. For instance, SVG files are scalable vector graphics files, so they obviously are intended for representing vector graphics. The big ones for raster are PNG and JPG. The PNG format and the JPG format are both raster graphics formats, but they use different methods for doing the compression. Generally, if you're doing things like photographs and other things where you have noisy data, so sort of real-world scans and photographs, the JPEG format usually gives you better control of the compression, so you can choose how much quality you're willing to sacrifice in order to make the file small. The PNG format is pretty good for some things. It's useful often for things that are drawings, where you have large areas that are all uniform color, and they compress that sort of low noise image a little better. Either one works pretty well, and doesn't really matter too much which one you pick. Whichever one is sort of native to the tools you're using is probably the one to use. I generally have found JPEG superior for what I'm working on. The vector graphics, there's a problem. SVG is a great format, except for it doesn't include size, it's scalable. The problem with the SVG format is that LaTeX doesn't understand it. And so LaTeX can't include an SVG file directly in as graphics. And so there's another format I use, which is PDF format. Now, PDF format is a really huge format with lots of different things in it, and it can do both vector and raster graphics. There is no point to doing raster graphics in a PDF format because PDF's compression of raster graphics and stuff is not really all that good. You're much better off using PNG or JPEG for raster graphics. But PDF can do a direct translation of vector graphics from SVG. You can even find tools that do vector graphics directly into PDF. And LaTeX does understand PDF, at least to the extent that it knows how to put PDF files into generating an output PDF file. So what I end up using for my graphics is PDF format for all my vector graphics, because LaTeX understands it, and usually JPEG, occasionally PNG, for my raster graphics. Okay, for the vector graphics, generally you're producing the graphics directly with a computer program, though. I have sometimes drawn some SVG stuff directly by hand. It's a human writable language, but that's only for really small things. Most of the time when I'm using vector graphics, I'm producing them from a program. And some of the programs that I use, there is a drawing tool that's at draw.io on the web that allows me to directly produce block diagrams. So that is what I've used for essentially all the block diagrams in the book. Draw.io has advantage over many other web tools, and it lets you keep your files on your own machine. So you can have them on your own device. You do not have to have them stored in some commercial device, some commercial cloud server that may go away. So you can keep the files on your own machine. They also, if you're using it with Google Drive, allow you to do shared editing of the diagram. And so that may be handy for those of you working on a block diagram as partners. If you share the underlying Google Drive document, you can both use Draw.io to edit that drawing. For schematics, Draw.io is really not very good. It's got a schematic capability, but it's terrible. It's great for block diagrams. It's terrible for schematics. It just doesn't have a good selection of parts, and the parts that it has got are poorly drawn, so the schematics look ugly. What I recommend for that is a different free tool called Schemit, and that one is available from a company called DigiKey. And DigiKey is a distributor of parts, and the Schemit tool is designed to integrate with the DigiKey catalog, but you don't have to do that. They've got a lot of parts there that you can just use in ordinary ways. You do not have to buy things from DigiKey in order to use it. However, it does have the advantage because they've monetized it by integrating it with their parts catalog. You don't have to worry about them in a year or two saying, oh, screw this, we're going to start charging for it, the way a lot of the other schematic drawing tools that I have tried using in the past have done. Is they started out as free tools and then said, you know, we're not making any money. We're going to start charging for this. And generally the results were that I stopped using them because they were not worth the price they wanted to charge for it. It was usually subscription fees that were, you know, for the amount of schematic drawing I do, they just weren't cost effective. So Schemit is a pretty good drawing tool. It will produce its output in both SVG format or PDF format. I have had some trouble with their PDF format in that sometimes they get the boundaries of the bounding box wrong, and that causes some problems with clipping off parts of the image or things not getting scaled quite right. So I've taken to using Schemit to produce an SVG file and then used another free tool to convert the SVG to PDF, and that is the tool Inkscape. Inkscape is a not very friendly drawing tool that uses SVG as its native format. So it will normally produce drawings in SVG, but it's got the capability of exporting them as PDF also. So I generally do scheme it and then go through Inkscape to produce my schematics. However, for this class, that's probably too many extra steps for the tiny differences it makes. So you can use Schema to directly produce the PDF, and that'll be good enough for this course. Okay, so block diagrams and schematics are two of the main drawings that we include in design reports. The other ones tend to be graphs, and for that part I've mainly been using GNU-plot and sometimes matplotlib in Python. Both of these can produce PDF vector graphics. And you want to produce PDF vector graphics from them. You do not want to produce PNG format. PNG format is possible from either of these, but that produces a large raster graphics thing, which when you try to zoom in to read the small fonts and stuff, just the information isn't there. It's blocky and really things get fuzzy when you try to scale photos, because the assumption for both PNG and JPEG when you're doing raster graphics, the assumption is there's some sort of continuous image like a photograph, and that when you scale it you can blur things, or it just doesn't work very well if you've got a sharp black and white sort of, or color and white image which has got very sharp lines. These compression schemes assume that that very high spatial frequency information is just noise, and in line drawings like the plots and stuff we do, it isn't. It's the high frequency information is what gives us that crisp, looking like a real plot sort of effect. So I use GNU-plot or matplotlib, producing PDF output. Okay, one thing is if you do have photographs, and I do include photographs often in the book, and you probably will want to include some in your report, the problem is this bigness. I have to look at the reports often with a grading tool like the Speed Grader in Canvas, and it's got a terrible PDF viewer that gets really, really slow if it's got a huge file to deal with. And I've had students turn in 10-page design reports that are bigger files than the entire textbook, and they're just impossible to grade. So absolutely essential that if you're going to include a photograph in any of your reports, that you take the time to scale it, downsample it, and do compression on it. And there's lots of different tools to do that. You can find thousands of them on the web. You can find lots of free tools on your phone even. But some things to watch out for there is your pictures probably shouldn't be bigger than 600 pixels by 400 pixels. Now, the photographs you get off of a decent phone camera are much, much larger than that. And there's no point for the purposes of design reports to having that much resolution, because nobody's going to see it. You're not doing something that's, you know, a professional photographer would envy anyway. So 600 by 400 is a good typical size to do for if you want a good crisp image in your report. Take the time to crop your image. Don't have, oh, I've got this little thing here and this huge piece of white background, or the blanket on your bed or something, because that just means that your image is tiny and hard to see. Crop it, and if you crop it down to like 600 by 400, it doesn't have to be exactly that shape, but in that size. The cropping and sometimes rotating, sometimes improving the lighting as a result of the standard photo editing sorts of software will do a lot towards making both the image easier to see and reducing the size to a point where your file is no longer ludicrously big. So do this before you incorporate it into your LaTeX file. So you have your original image, and then you have one that's scaled, cropped, maybe cleaned up a little bit. Don't spend hours on editing the images. I mean, I did on some of the ones in the book, and it's not necessary for design report to waste that much time. It's mainly a way to avoid doing real work. But do spend some time to make sure that your image size is reasonably small. And if you output it in JPEG format with moderately good quality, usually there's some control over the export from whatever your tool you're using about how high a quality you want. There's a quality versus size trade-off. But if you do a moderately high quality JPEG image, your files with this lower resolution, your files probably won't be more than about 100K to 400K. And that's small enough that you don't have to worry about it. You can put lots of photographs of that size into Design Report without stressing any of the tools like the grading tools. If you put in 4 megabyte images and you put in a few of those, then you're stressing the tools. They really do not like huge files. So keep your files, keep your resolution down, crop so that this resolution gets you this part of the image that you really want the reader to see, and put it out in JPEG format and you'll probably do fine. The same thing also applies if you're trying to scan your homework to submit handwritten stuff for homework. Use a good scanning tool and make sure that the file size is not ridiculous. We don't need 600 dots per inch to read your handwriting. Keep the scans down to a reasonable size. And again, the standard scanning tools, whether you're using a flatbed scanner or a phone camera as your scanner, do allow you to keep the file size reasonable. Okay. There's some stuff in the book about how to do things like doing this use of Inkscape to convert an SVG file to PDF file. Read it if you decide to go that route. There's some stuff about how to include these things in LaTeX. I talked about that in the previous video also. Do try incorporating some images into your documents. You're going to definitely need to do block diagrams and schematics, and most of you are going to want to do a photo or two along the way also. And these are all useful skills for later on reports when you're doing them for even non-electronic sorts of engineering reports. You're probably going to have to incorporate some sort of drawn images, some sorts of plots, and quite likely some sorts of photos. So these are all things that you should practice and get good at, even if you're not primarily interested in electronics as your field.